In this module, I shall characterize compactness in terms of open covers. So without further ado, let me state the main theorem that we are interested in. A set K subset of R is compact if and only if every open cover of K has a finite subcover. Let's prove this. Proof. Let K be a compact subset of R. Okay. Let O be an open cover of K. We now have to show that there is a finite subcover. There is a finite subcover of O. Now, how do I show that there is a finite subcover of O? I have to use this Lebesgue number property. We know that with respect to K, O has a Lebesgue number. So let delta greater than 0 be a Lebesgue number for O with respect to K. This means for all x in K, B of x delta is a subset of some OX which is an element of O. This is the definition of a Lebesgue number. Okay, how does this help us? Well, pick some x1 in K. Okay, suppose B x1 delta does not contain K. There are two possibilities. Either this single open set B x1 delta, this single ball itself contains K, or it doesn't. We are assuming that this single ball doesn't contain K. Then choose x2 in K set minus Bx1 delta. Choose some point of K which is not there in Bx1 delta. Continue like this. This means having chosen x1 to xk, let xk plus 1 be an element of K set minus Bx1 delta union Bx2 delta union Bxk delta. Okay. Now if this process terminates, we are done. Why are we done if this process terminates? Well, the only way this process can terminate is if K is a subset of some Bx1 delta 1, or not delta 1, just delta, Bx1 delta union Bx2 delta union union Bxk delta. That is, some finite collection of open balls cover the whole of K. But each one of these open balls is contained in some element OX1, OX2, dot 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 OXK. Remember, delta is not a Lebesgue number. So that means K will be subset of OX1 union dot 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 OXK. And we have found our required finite subcover. So the only possibility is this process doesn't terminate. Process doesn't terminate. Okay? Which just means we have found a sequence xk. Let me not call it xk, let me call it xn. We have found a sequence xn in K. Okay? Not only have we found an xn in K, this xn plus 1 is not an element of B xn delta, right? That's exactly the way by which the next element in this sequence was chosen. Okay? Hence, xn cannot be Cauchy. Cannot be Cauchy. Right? For this choice of delta, xn plus 1 and xn can never be delta close, right? By the very way by which we have chosen this xn, which means, this means not only can xn not be Cauchy, this means any subsequence cannot be Cauchy as well. Why is that the case? Well, it's because any given term of the sequence is at least delta distance away from all the prior terms. So the same argument will tell you that any subsequence also cannot be Cauchy. Hence, no subsequence of xn can converge, which this contradicts the fact that K is compact, right? Compact means any sequence has to have a convergent subsequence. We have just found a subsequence that does not converge. So what we have shown is that if K is compact, any open cover will have a finite subcover. Now for the converse, let K be a set such that any open cover has a finite subcover. Okay, we have to show that given a sequence xn in K, there is some convergent subsequence. Okay, how does one do this? Well, this proof is a bit tricky. So what I do is I collect together all the points xn and put it as a set. Okay, let me call this set S. The terms of this sequence, let me call it S. Now let S prime denote the set of limit points of S. Okay, let S prime denote the set of limit points of S. Note that S prime intersect K if non-empty will produce for S produce for S the required subsequence. Required subsequence, or rather required convergent subsequence. Convergent subsequence. Now this is left as an exercise for you. What we are doing is, our aim is to produce a convergent subsequence of Xn. We are looking at all the limit points of S. The claim is, if one limit point of this set S is also there in K, this will allow us to produce a subsequence that is actually going to converge to a point of K, which is what we want to show. Okay? Hence, no limit point of S is an element of K. Is an element of K. Okay? Now what does this mean? This means that given any X in K, we can find delta X greater than 0 such that B of X delta X intersect K contains at most one point of the set S. Again, exercise. So this proof, I am leaving 2 steps to you in the hope that you will get practice in thinking about the various concepts and the relationship between the various concepts. Okay? Now let me give you a hint for this part. This is because we are assuming that no limit point of S is an element of K. That's the key. Okay. Look at the collection O, which is equal to this Bx delta X as X runs through K. This is the collection of all such open balls. Okay? Clearly, as X is an element of Bx delta X, it is no shock that it follows that O is an open cover of K. By hypothesis, O has a finite subcover. Okay? This means some Bx1 delta x1 union Bx2 delta x2 union Bxn delta xn, or let me not use n, xm delta xm, this collection contains K. This forces the set S to be finite. This forces the set S to be finite. Okay? Because each one of these balls, Bx delta x1, Bx2 delta x2 Bxm delta xm, each one of them contains at most one point of S. Okay? So this forces the set S to be finite. Then it is easy to see that Xn has a constant subsequence. Constant subsequence. And we are done. And we are done. Okay. So, we have now characterized compactness in terms of open covers. Let me make the general remark that historically, the proof that any closed and bounded subset of R for such a set, any open cover has a finite subcover, that is what was classically known as the Heine-Borel theorem. I have stated what I call the Heine-Borel theorem slightly differently. I have characterized compactness in terms of sequences, which I believe is a much better approach at such an elementary course. This is a course on real analysis, and you have just watched the module on equivalent notions of compactness.